So far we have defined combinations and illustrated them with a few examples. Now we're going to look at some notes on combinations. The first thing is the entries in Pascal's triangle are binomial coefficients. If you haven't seen Pascal's triangle before, it looks like this. And what you have here is the first row is a 1, followed by 2 1s. And the next row is 1 2 1. The next row is 1 3 3 1, 1 4 6 4 1, and it goes on and on. A couple things to notice here. First of all, Pascal's triangle is symmetric about this vertical line. The second thing to notice is you always have a 1 at the far left and the far right, so we're going to see how we put together the next row in Pascal's triangle. And it turns out between those 1s, you simply add the two elements that are above. So 1 plus 4 gives you 5, 4 and 6 gives you 10, 6 and 4 gives you 10, 4 and 1 gives you 5. So there's the next row, 1, 5, 10, 10, 5, 1. Another thing, and I'll do this by writing off here on the far right, if you look at the row sums, they're kind of interesting as well. The first row sum is 1, then 1 plus 1 gives you 2, 1 plus 2 plus 1 gives you 4, 1 plus 3 plus 3 plus 1 gives you 8, and on it goes. And you can recognize right away that these row sums are powers of 2. One more thing that's a little more obscure about Pascal's triangle, if you run these arrows off at just the right angle, and take sums, well, the sum here is 1, sum here is 1. In this case, we get 1 plus 1, which is 2. In this case, we get 1 plus 2, which is 3. And in this case, we get 1 plus 3 plus 1, which is 5. And if you consider the series 1, 1, 2, 3, 5, etc., you'll notice that those are the Fibonacci numbers. So that's another thing about Pascal's triangle. And actually, I had my son at a pool party when he was in the 3rd grade. And there was a young man in the pool who his parents came to me and said, you know, he's really good at math. We don't know what to do with him. And I thought, well, 8 years old, how good is he at math? And so what I did was, his name was Paul. His parents brought him to me, and so I said, have you heard of Pascal's triangle? And he said, yeah, I've heard of it. And he said, you know, I can't figure out why those digits, if you can concatenate each row, you wind up with powers of 11. So here's what Paul had to say, is that each row is 11 raised to a power. And I looked across and I said, that's right. 1 is 11 to the 0 power. Then 1, 1, concatenate those together, there's your 11. And then 11 squared is 121. And 11 cubed is 1,331, etc. So he's right. These rows, if you concatenate the digits together, you get powers of 11. But then he asked me, why does this break down in that row right there? And I told him the reason is you get 2-digit numbers. And that's why the 11 to the power. By the way, this 11 to the x power, you can think of it as 10 plus 1 raised to the x power. And in what you see in the next note here, you'll realize why that's the case. Second note is the coefficients in the expansion x plus y to the n power using the binomial theorem are combinations. So for example, if you want to take x plus y and raise it to the 4th power, that's going to be 1 times x to the 4th plus 4 x cubed y plus 6 x squared y squared plus 4 xy cubed plus 1 y to the 4th. Well, if you look at the coefficients here, 1, 4, 6, 4, 1, that is one of the rows in Pascal's triangle. So this is why it's referred to as a binomial coefficient. The general statement of the binomial theorem is if you want to take x plus y and raise it to the n power, you get this summation, and there is your binomial coefficient, which of course is related to combinations. Now on the next page, here are 3 more notes on combinations. The first one is symmetry. N choose R is the same as N choose N minus R. And what you're going to see is if you ever have 6 choose 2, that will be exactly the same as 6 choose 4. That's easily seen by the definition of the binomial coefficient. The second one here is that N choose R is N minus 1 choose R plus N minus 1 choose R minus 1. This is the way when we were doing Pascal's triangle that we formed the nth row by adding the 2 values in the n minus first row that were above it. And finally, here is another miscellaneous result. If you take this summation of the product of 2 combinations, you get this particular quantity. Now, N choose R is defined to be 0 when R is less than 0 or if R is less than N. So, for example, if you see 6 choose negative 1, it will look kind of odd if you ever see it, but that's defined to be 0. Or if you see something like 6 choose 1,000, that will also be defined to be 0. These don't make any sense in terms of counting problems, but will show up occasionally in mathematics. Finally, the last one, the binomial theorem can be extended to a multinomial theorem to handle the expansion of expressions like x plus y plus z to the 5th. So the binomial theorem handled x plus y raised to the 5th power, but if you want x plus y plus z raised to the 5th power, then you want to know what is known as the binomial, or I'm sorry, the multinomial theorem. And the coefficient when expanding x1 plus x2 plus xk to the n power is n choose m1, m2 up to m sub k, which is defined in this fashion. And you may notice that that is very similar to what we hit just recently in terms of non-distinct permutations.